I will introduce our next speaker is Professor Lu. So Guoxing Lu is a professor of impact engineering. So he's a director of the Impact Engineering Lab and also director of a joint research center in China. So his research interest is in the fundamental impact mechanics of structures and materials, as well as the applications. So he has authored the two monographs on the topic of energy absorption and the plastic analysis of structures and the materials. He has published more than 250 journal papers with over 8,100 citations and H index 47 from Google Scholar. So he's an associate editor of the International Journal of Impact Engineering and a member of the editorial board of the International Journal of Mechanical Sciences, Thin Wall Structures and the Composite Part B. So Guoxing Lu did his BEng in Jilin and the MSc in Cranfield in UK in automotive engineering and obtained his PhD from the University of Cambridge in structural mechanics. So he previously held faculty positions at Nanyang Technological University, Singapore. Professor Lu.
Thank you very much for your kind introduction, Zhongwei. It's my great pleasure to present our recent work on origami structures. I'm grateful to the organizers for their kind invitation, especially Professor Zhongwei Guan and Dr. Taneji. So the work has been conducted over the past maybe around 10 years in collaborations with a number of researchers, including Professor Zhong Yu from Oxford, Professor Dora Karajizova from Bulgaria, Professor Yin from Tianjin University, and some of my former PhD students and current PhD students. So I'm going to give a brief introduction first on the energy absorption. This is common to all, but also I just briefly mentioned it. And then I'm going to talk about quasi-static compression of origami structures and materials, followed by dynamic compression. So why energy absorption of structures and materials? One example is injury of human beings, the head injury. So if we look at a common traditional head injury criterion, we plot the effective acceleration as a vertical axis, and the horizontal axis is a duration during which the brain or human head is subject to the acceleration. So the line, it's a double logarithmic plot. So the line here defines the boundary. Safe, and outside this line, the brain will be subject to severe injury. So in other words, the magnitude of the acceleration or deceleration should not be too high, or the duration cannot be too long, okay? So that indicates that if we try to prevent a human brain from damage, we should limit the maximum acceleration or deceleration, and also try to limit the duration. So it indicates that when we design an energy absorbing structure or material, we want to make sure that the force is a constant force and over a long distance or long stroke. The reason being that if the force is too excessive, from Newton's second law, the acceleration, which is equal to force divided by mass, will be excessive. And so ideally, when we design a structure or materials, we should have a constant force over a long stroke. Just as an example of energy absorption behavior of a structural component. Now, this is a thin-wall structure, a circular tube on the axial loading. So if you crush it, you measure the force as a function of displacement. Typically, you will have, of course, a linear elastic stage followed by a peak, then a sharp decrease in the force, and then the fluctuation of the forces corresponding to the folding during the collapse. So in this case, you will see that the peak force is very high, which is undesirable. So we should try to limit the force. And also there is a fair bit of a fluctuation of the forces over long stroke over the whole displacement. And also we try to eliminate this. So therefore, our aim is to design structures or materials so that when we crush it, we can have more or less a constant force over a long period of displacement. So that was the introduction for the energy absorption. Now, if I introduce the concept of origami, origami is actually a Japanese word. Ori means folding in Japanese, and gami is a paper, a piece of paper. So on the right-hand side, you can see that we can start with a flat sheet of paper and then inscribe some creases on it, and then we can fold it or unfold it freely. So in Japan, that has been a traditional art. And over the last decade or so, engineers start to adapt this concept for our engineering applications. And one example is shown below by Professor Laurie Howell from Bright Young University in the States, whom I met a few times. Now, Laurie actually designed a foldable shield made of Kevlar. So this is portable, and we can transport it to different places. And that acts as a shelter for policemen, for example. And once it's done, then we can fold it and pack in the car and drive away. So this is one application of origami structures as a deployable structure. Our interest is slightly different. We try to apply the concept to design so-called metamaterials. A metamaterial is an artificial material from which we design the, if you like, a microstructure and put them together. Then overall, globally, we can obtain or achieve certain properties which are otherwise impossible to achieve. So for us, we are interested in the energy absorption of these materials. So for example, we can start with a unit shown in A here. It's a flat piece of paper, and then we can inscribe certain creases. The solid lines showing the mountains, and the dotted lines are the valleys. And this is one of the simplest form for folding, and it's called a mirror pattern. So we can fold it along the creases to form a unit on the right-hand side here. So this is just one unit. And conceptually, if we can assemble all these units to get a block underneath, so in principle, we get a piece of metal material. So from geometry, this unit cell has got a few parameters: the side length A and the side length B, and the angle alpha. This alpha is within the plane first. So these are the three variables to start with. Then there is a fourth variable, which is a theta. Theta or gamma here, which is an angle between the two folding planes. So these describe how much I have folded this unit starting from a flat sheet. And once I know AB, alpha, and the theta, from geometry, I can get to the overall size of the length, width, and the height. So our interest is, if we have such a unit and we crush it, what happens? So on the left-hand side, we did a very simple finite element analysis, I'm sorry. And if you see the animation on the right-hand side, we can crush it. And we can see that a lot of plastic deformation actually occurs along the crease lines here. And the rest of the material does not undergo much plastic deformation. So that encourages us to make use of plastic analysis for this unit. So because it's a larger deformation, the elastic deformation is small, and we usually ignore the elastic deformation. And also for simplicity, we assume the material behaves like a perfectly plastic material, which means that the yield strength does not change with the strain. So we can write down the work balance equation for that unit. On the left-hand side, it's the force times the increment of the displacement in that direction. So that's the work done by the external force during an increment of a displacement. On the right-hand side, we assume that the work done externally is dissipated by the plastic bending along the hinge lines, along all the creases. And these are represented by two terms on the right-hand side. And the full plastic bending moments, as we all know, is simply equal to the yield stress of the material times the thickness of the sheet squared divided by 4. That's the bending moment per unit length. So we can do a bit of mathematical manipulation, and we realize that the angle theta, which defines how much we have folded, it's actually corresponding to the displacement globally as well. So therefore, we can get a force as a function of theta, which also is a function of displacement. The other important parameter is what's the maximum displacement that we can crush. So that is WF. Again, it's purely geometrical. So from geometry, we can work out this expression. And in terms of strain, the densification strain will be equal to the maximum displacement over the initial length, W0. Okay, so that gives us the densification strain. So if we plot the force against the displacement, and the dotted line is the analytical results for that unit, and the solid line corresponding to the results from the finite element analysis, we can see that the agreement is fairly good for the most part of the force displacement curve, except towards the end, the actual deformation is slightly different from what we have assumed using the plastic analysis. So there is sort of contact between the faces on the sheets, and therefore from the finite element analysis, the force is larger. But overall, in terms of the force displacement, the agreement between the analytical results is very much is pretty good with the finite element results. And we can also look at different values of parameters and then see the results. So overall, they are pretty good. And then we try to apply this method to the whole block of material. So that is a relatively easy task, because we just need to count the number of cells and count the number of hinge lines. Then we can figure out the plastic bending energy for this piece of material. So on the right-hand side, actually we made this piece of material. So we had 4 layers of this origami sheets and then glue them together. It's made of aluminum. And then we do a quasi-static compression test. And on the left-hand side, we have a force displacement curve. So the solid line in blue is the test results, and the solid line in black is the analytical result. Again, our very simple analytical result agrees fairly well with the test result, even though we have made assumption of a rigid, perfectly plastic model. Now, we are all very familiar with cellular materials such as honeycombs, foams, and so on. So naturally, when we define these mechanical properties of such materials, we quite often make use of something called a relative density. So we were very interested in calculating the relative density for this origami metamaterial. And then surprisingly, very interesting, we found out that the relative density, which is plotted as a y-axis, vertical axis, as a function of folding, the angle of folding. Actually, it's not monolithic result. So corresponding to one density, I could have two geometrical states to have this density. So that is quite an interesting and unique feature for this metamaterial. And similarly, in terms of densification strain, it's not exactly a one-to-one relationship with a relative density. And then we also work out the force, initial collapse force, as a function of the relative density. Again, because there is no unique one-to-one relationship, so we can have this sort of set of curves. And then what we did was we look at the specific energy absorption, which is energy absorbed per unit mass. And we can integrate the force over displacement to get the energy and then divide by the mass, which is the density times the volume. So we can work out this quantity. Now, our interest was how this material is compared with, for example, honeycomb. And then we look at the expressions for a usual honeycomb in plane, under in plane compression. And then we look at the specific energy for the honeycomb. And then we also define something called efficiency factor, which is the specific energy times the density of the solid of this piece of material and the yield strength of this material. That is really to eliminate the variation caused from the parent material property. So when we did this efficiency factor as a function of relative density, the red line is for honeycomb, and the points, solid lines, these are for the origami metamaterials. So once we have done the first plot, I was quite disappointed in the sense that all our points, more or less all, the points for the origami metamaterial are below the honeycomb, which indicates that this material is not as good as the honeycomb. So we tried again with the other values of for geometries, and interesting enough, we found out that under other certain geometries for the graph on the right-hand side, we can see that the behavior for this material could be better than honeycomb. So I was not, just to show this concept, so we did finite element analysis for this piece of metal material. And we get this black solid line here on top. And for the honeycomb, we get this red line here. So that demonstrates that sometimes we could get a slightly better performance. So that was for compression in one direction. Then naturally, we were thinking, how about the compression in the other direction? So we took this nominally the same piece of material and then crush it in the other direction. And this is what happens. So on the right-hand side, we plot the force as a function of displacement. And you can see that experimentally, the red line is shown here. And the blue line is from the finite element analysis. And again, from the simple geometry, we realize that we can work out the analytical solution quite easily as well. So the analytical solution is this dark square line here. So we can see that's interesting enough. Again, the analytical results shows very good agreement with the the other test and the finite element results. And we also look at the crushing in the other direction, in the third direction. And this is what happens. And we plot the force as a function of displacement. And again, we get experimental and finite element results. And initially, this material behaves like a piece of block material until towards a later stage, you can see the localization and also buckling and so on. So at least for the initial parts, then our analytical solution for this direction seems to be okay, even though it's not as great as for the other two directions. So again, we can look at this approach for different values of falling angle and so on. So from finite element analysis, also our analytical results, we seem to have a very good agreement for the forces in other two directions. So that was for the quasi-static case. Now the question is, what happens if we crush this block of material under impact loading? So we started with a unit cell. You can see the animation from the finite element analysis. So when we look at this one, we can see that the force required externally to deform this unit cell and is composed of two parts. One is it's required to overcome the quasi-static strength, which is FQS. Now the other part is really to enhance the velocity of this piece of mass from initially 0 to a velocity, constant velocity later on. So then we apply the conservation of momentum. So on the left-hand side, it's the impulse actually. It's the dynamic force Fd minus the quasi-static force Fqs. And the difference, if we integrate over a time interval, and this is the impulse. This impulse is used to increase the momentum of this cell, which is the mass times the velocity. The initial velocity for this cell was 0. And of course, the time interval is T1 minus T0, which is given as the cell size divided by the velocity. So we can do a bit of manipulation. We in the end find out Fd, which is the dynamic force, turns out to be equal to the static force, quasi-static force plus a second term. Now this second term is proportional to the density, rho 0, and the area of the cross-section, and then nominal cross-sectional area, then divided by the log strength epsilon d, then also times the velocity squared. And this second term actually represents the inertia of this piece of a unit over mass m. So we can plot the force as a function of displacement from the finite element analysis, the top one, and as a function, compared with the analytical solution. So analytical solution is given in red. That is at the impact force. Now the force below is really the force at the supporting end. We also call it distal end. And again, the finite element analysis is given by a continuous blue line, and the other one is analytical. So we can see that the force from the FEA fluctuates a fair bit, but overall the average force seems to agree with our analytical results. So that was for the unit cell. Then we wondered what happened if we have a block of a so-called metamaterial made of this sort of unit cells. So if I do an impact test, now this is a compression test. We used a VHS system, which is capable of applying a constant velocity up to 10 meters per second. So this was done for 10 meters per second, and we use a high-speed camera to take a photo of this, and we can measure the force and so on. So from the finite element analysis, when the velocity v is equal to 5 meters per second, we get the outputs for the force at the impact end and the force at the support end. Now the force at the support end is in red, impact end is in black. And when we look at the deformation mode, so we can see that actually deformation is localized, but starting from sort of a supporting end a bit. But the two forces at the impact and the support end, they are very close, indicating there is not much inertia involved. And if we increase the velocity, for example, to v equal to 10, similar behavior occurs, except the force at the support end had a bit of delay. And if we increase the velocity a bit more, v equal to 30 meters per second, we start to see that actually deformation starting from impact end from the top, and then later on towards the end at the support, it also has a bit of a deformation as well. And if we increase the velocity to 50, we have something like this, and the deformation is very much localized at the impact end. And also the two forces at the impact and the support end, they are very different now. And if we increase the velocity, for example, to 100 meters per second on the right-hand side, the impact force and at the impact and also at the support end are shown on the right-hand side. And our analytical results again is given as a constant force, given in red. You can see that overall the analytical result is able to capture the average force. So that was for the case when the velocity is a constant after the impact and is kept a constant. So if we had another impact scenario with a mass and also initial velocity, so in this case here, during this crushing process, the velocity will decrease. And then you can see that the force actually decreases when the displacement increases. So similarly for other velocity, I should not get into the details. And we look at different densities for these metamaterials, similar behavior occurs. So I should sketch it. So that was for sort of a uniform metamaterial. And then one of the advantage of this origami metamaterial is we can change the geometry and to have a certain behavior. So one feature that we could do is that we can change the values of geometrical parameters for different layers. So then effectively we could have a so-called graded metamaterials. And we tried this, we 3D printed this metamaterial, and then we even crush it. So that is for the quasi-static case. So this is made of a polymer, it's not made of metal. So we crush it on the right-hand side, we get the force displacement curve. And the top one was for the uniform, and the bottom one was for the graded material. So what I would like to highlight is on the curves on the right-hand side, we can see that sometimes there is a big fluctuation. So by adopting certain gradients into this material, we can have a sort of a more or less flattened force displacement curve, as shown as this red circular curve here. So that offers a way for us to tune this material behavior simply by changing the geometric parameters.
Hi, Professor Liu. You need to wrap up.
Okay, sorry. Sorry. So I will finish soon. So we also did some impact tests, and what the highlights for this one is the impact test gave us a fracture of this behavior, okay, rather than sort of ductile behavior. So this is something we really have to watch out. So that was for the metamaterials and structures. Then we also adopt the same concept to design structures. For example, on the right-hand side, we introduce initial imperfection, if you like, to eliminate the peak force. And also at the bottom here, we can have a sandwich panel made of origami core and to look at the energy absorption. So that was for the mirror pattern. And there are other origami patterns. So during the lockdown in Melbourne, managed to follow some and I did some crashing of different units. You can see that we can overall get different geometries and kinematics and so on. So if I just try to summarize, I'd like to just emphasize that by adopting this origami concept, we can design, the concept offers a new dimension for us to look at designing of materials and the structures simply by changing the geometry. And also our traditional structural plasticity theory can be successfully applied to capture the energy absorption behavior of such materials. And also the impact mechanics seem to be valid as well for this. And one of the interesting parts for this origami structure is it's kind of scale independent in the sense that it's purely geometrical. So we can make structures at a micro level as large as even a space structure at a mega level. So this is a picture of Swinburne University, and at the back, it's the city of Melbourne. So I invite you all to visit us in Melbourne in the near future. Thank you very much.
Thank you, Professor Lu, for your very interesting talk. Now we have some time for questions. So I have a question from Miss May, and so she asked this Mayoro folds along for its easy opening, easy closing properties. What made you choose this structure for your study?
Oh, this is the easiest cell, actually. So we thought we start with this unit. And as I show you to the end, we can have other units, even for twisting unit and so on. So, but they will be more complex geometrically. So we started with a simple geometrical one first. So that was the reason only.
Good. Any more question?
Thank you, Professor Lu, for your nice presentation. A question is, what the application of this material rather than energy absorbing? If there is any chance to utilize in other application than this?
That's a very good question, actually. And one of the reasons that I started this one is, intuitively, one could say, actually, sometimes it may not be as good as even honeycomb. But for this material, you can see that all the cells are interconnected. And therefore, it's like an open cell form, okay? Unlike a honeycomb where the cells are isolated. So that really offers an advantage in terms of, for example, other properties, heat transfer, or even some fluids, or some acoustic effect. Actually, I have a PhD student working on the acoustic effects of this kind of material. So when we design the structure for some sort of multi-performance, in addition to crushing behavior, mechanical property, if we are also worried about thermal behavior of some salvage structures or properties, it may offer some other options for us to fine-tune or design such structures.
So the acoustic, specification is absorb acoustic or isolated acoustic, or what is doing exactly?
For the acoustic, actually, this structure is adjustable, so we can deploy this structure actually relatively easily. So the acoustic property is a function of the geometry, how much we fold it. So the idea is according to the external requirements, sometimes we may be able to tune the acoustic property by changing the folding, by folding this material more or less, and so on, we can get this. Or sometimes we can even drill some holes in the structure to guide the acoustic behavior.
Do you have a research in this area? I mean, just study the band gaps of acoustics and these things. At the metamaterial
Exactly.
level?
Yes, that's right. Yeah, actually, my student has written a draft paper, but I've been delaying for months actually in revising it. So
actually, we have a team. We have a team who study this, but it's not these structures. The same what you are doing. Yes.
Oh, I see. Okay, that would be very interesting.
Yeah.
So we look at the bandwidth.
Dr. Lee now he can tell you about it. I mean, offline or later or.
Sure.
Sorry.
Yes. Yeah, that would be very interesting. Yeah.
That's good. I have earlier asked you a question. So she said she's interested in the fabrication of the metamaterials. So what 3D printing technique was utilized to fabricate them?
I see. For this one, actually, we use two different printers. One is for polymer, the other is for metals. And for the metals, again, it seemed to be too brittle, the product. So we didn't study much, but we concentrate on the polymer side, which turned out to be okay for the quasi-static case. But for the impact case, as you see, it tends to be brittle, which absorbs much less energy. So it's just a conventional material. But interesting enough, some research in the US, for example, they had a much better 3D printing technology or using laser or two-beam lasers. And then they can manufacture material at a very much a smaller scale and to obtain the much better overall properties in terms of Young's modulus and also even energy absorption. Yeah. So if you have a better 3D printer, that would be great.
yeah, that's good. And I think the Professor Omar Nabilina has a question. So,
yes.
So Omar.
Yeah, I want to ask you, Professor, about the regarding the origami structures. Could we use it in high dynamic applications, for example, like blasts and projectiles?
Certainly, that's what we also are trying to study, actually. In terms of the projectile, then we want to make sure that the bullet does not penetrate around the area, which is like a hole, a void area. But so the cell size cannot be too large, in comparison with the bullets or projectile. For blast learning, we also look at this. We look at on the quasi-static case on the uniform pressure, the behavior of certain this sort of a structure. Yeah.
So do you think, like, if we put the lattices very small, just similar to the diameter of the bullet, so it could do the job, or still?
It could do. The only thing is that we are still looking at this whether it's better than honeycomb. But I'm confident that at least it should be comparable to honeycomb or even metaform and so on in terms of this sort of performance. But whether it can be better, I cannot say at this stage.
Okay. Thank you.
Good. Maybe one final question, and let me say, I believe this could be improved by post-processing, such as a thermal treatment, because it's brittle, more brittle issues. Is Professor Lu?
Yes. Again, it's a very good point. Actually, for metals, in terms of instead of 3D printing, actually, we also try to use a stamping technique, more like a traditional stamping with 3D printing the molds, die, and then stamp it. So afterwards, we try to heat treat it by annealing it to release residual stresses and so on to enhance the ductility. But there is a limit to how much we can achieve. So it will be interesting to extend this.
Good. Thanks so much, Professor Lu. So I have to move on.
Thank you very much, Professor Guan. Okay. Thank you all. Yeah.